Thank you for coming today. My name is Hori. I'm senior and I'd like to talk about my homemade flight computer. So why rockets? So some of you may have already know that I have made some rockets for the past 2 years at Williston. And I started Rocketry Club with my peers last year and managed to launch 2 homemade rockets from Galbraith Fields and had 2 successful flights, sort of. And it has been 51 years since Apollo 11 touched the surface of the moon. And it has been just 60 years since the first human went to space. And it's crazy that we think about how many private rocket companies there are right now. And in recent years, many billionaires are eager to take a trip to space using a commercial rocket and commercial spaceships. And the most fundamental reason why we have heard of space travel or commercial rockets, commercial spaceships, is that the price to launch a rocket has decreased by a lot, mainly by a factor of 2, reusability and productivity. So take SpaceX for example. They believe that fully and rapidly reusable rocket is the pivotal breakthrough needed to substantially reduce the cost of space access. And the majority of the launch cost comes from building a rocket, which historically has flown only once. So it's like you spend a lot of money, like couple billion dollars for the rocket, but it's gonna be just wasted only one time. You throw away in the ocean or throw away into space, which is not really good. But the SpaceX has successfully had a rocket landed and recovered 92 times out of 103 attempts, which means that the price of a launch is the price of a fuel only. And also you can 3D print out almost any parts of a rocket. And this is an image of a company called Relativity. And this company is trying to 3D print every single part of a rocket just by using 3D printer, this is a fusion 3D printer, and it's printing a metal, and that is the biggest metal 3D printer in the world, and it's trying to print out from engine to everything just using 3D printer. So productivity is everything. So everyone's be like, that's cool. So I was like, can I do the same thing? And I did. This is a picture of my rocket. It's serial number 2. I used the blue parts are the ones that I use 3D printing. And this is a simulator that I have used for designing a rocket, which takes material and density and everything accountable. And this is how it looked before the painting. Well, it's actually big, as you can tell from the desk. And this is a video of the first attempt. It went pretty vertically, as you can see. If you take a look one more time. So the ideal situation of a model rocket is to go vertically upwards, and this went upwards because it was light, pretty light rocket. It only had a raw egg inside, so the mass of the rocket was only 600 grams. And the second launch that I had was not a success. It went a little bit, it slid down to the right. As you can see, it kind of like tilted towards right and came back. And this is an ideal situation because that means that the center of gravity and the center of lift is not really aligned perfectly. And thank God there was no wind, but if there's a wind, this rocket could have gone just the right way, which, there's like a town and a school around there, so I didn't want that to happen. So it was not a perfect launch. The rocket didn't have a flight computer, so as soon as you ignite the motor, it just goes by itself. And the trajectory was off and it was not vertical, which led to the rocket going missing into woods. Yet the rocket went into woods and I couldn't find it. That was a tragedy. And the altimeter also went missing, which was the most expensive component of all. So I came to this idea that I need a rocket that can control itself. So my question is it possible to build a model rocket using a 3D printer? Is it possible to build a flight computer using Arduino? Is it possible to control the trajectory of a rocket using Arduino? And if you combine all these questions together, that'll be, is it possible for me to do what NASA is doing with a little computer, Arduino? So I have to have a thing that can measure altitude and it measures inertial motion. So how to measure altitude? This is so the altitude can be measured with atmosphere pressure and use an air pressure sensor to determine the approximate altitude for the flight computer using a relationship between air pressure and altitude in pascals and meters. So the most of the altimeters used in this world are based on this equation. The altimeter on the airplanes, altimeter in the iPhones, they're all using this equation. And how to measure inertial movement. So this is a sensor. I have a little sensor on the computer that measures 3-axis accelerometer, which measures gravitational acceleration, and also it measures rotational velocity, torque. And in flight, any rocket will rotate about its center of gravity, a point which is the average location of the mass of the rocket. And then we can define a 3-dimensional coordinate system through the center of gravity, which each axis of the coordinate system perpendicular to the other 2 axes. So the rocket constantly moves every second, and because it's moving 3-dimensionally, you have to think about movement in different axes, and this is what is called yaw, run, and pitch. And traditionally, to analyze rotation, you need to have 3x3 matrices to represent a rotational vector because you treat each dimension x, y, z differently. But since the motion vector of a rocket is constantly changing because it's moving and the wind and everything's getting accountable, each rotational vector is also changing simultaneously. So if you want to calculate this, you have to have 3 different 3x3 matrices, which is a lot of computations to do in a small computer. So the idea of quaternion comes in, and quaternion is the equation expressed right there, and it holds a scalar as a 4-dimensional object. And in other words, you can move your vector with much less computation. So you don't have to have 3 3x3 matrices. You only have to have a complex number. You have to have a complex number and a vector, so it requires less computation and is a modern application used since late 20th centuries. And this idea also can be used for airplane as well. And this is what is going on. When rocket is in the air, it could be moving, it could be spinning, but it could be also rotating vertically as well. And also, to control the movement of the trajectory, you have to predict the future motion of the rocket. And this is called Kalman filtering. And Kalman filtering is a linear quadratic estimation. It is an algorithm that uses a series of measurements and produces estimates of an unknown variable that tend to be more accurate than those based on a single measurement alone. And that is what the Kalman filter looks like. So the true value, which is what I want. So I want my rocket to go perfectly vertically upwards. So that shows just a vertical line. And the measurements is what the inertial sensor is measuring. And I want to align that blue line into green line as close as possible. So the red line is what the common filter shows, and that's how the rocket controls itself with using a motor. And the graph on the left hand, the picture on the left hand side is how the common filtering is what is processing. Measurements is the sensors like inertial sensor and atmospheric barometer, and the computer processes every 10 milliseconds for the duration of 1 minute flight. So TVC, which stands for thrust vector control, and thrust vector control is the main operation of any kind of a flying object that can control its motion by itself. And the Saturn V rocket, which is the rocket that was used for Apollo mission, was guided by navigation, guidance, and control equipment located in the unit. And a space-stabilized platform measures acceleration and altitude, which is what the computer is doing. And the altitude of the vehicle was defined in terms of 3 axes. And this is a picture of Saturn V's flight computer, which is massive. It was 50 years ago. But all the equipment that contained in that massive flight computer is basically same as my computer. It measures elevation, it measures 3 axis motion and altitude, and everything else is just massive. So how does PID control work? So PID is the process that you want to use for thrust vector control. And PID stands for proportional, integral, and derivative. And this is a method of fixing of errors. Like as I said, the ideal situation is to have a rocket goes up vertically upwards, but it doesn't really go that way because maybe the center of gravity is not really perfectly aligned as the simulator showed, and the air density and everything could be accountable. So this is a way how the computer processes and removes all the offs from the air as much as possible. And this is also the way that the Tesla is doing for autonomous driving. And most of the any kind of autonomous driving or any kind of AI-driven software is using this method for going forward or any kind of assigned movement. And that is the equation for a formula for the PID control. And the picture on the left-hand side is the TVC. It has X, Y plane. It has 2 actuators that is attached vertically, and it moves the motion of the rocket X and Y plane, so it can control. So as common filtering is processing the situation, and when the rocket is a little bit tilted, which is measured by the inertial sensor, the actuator moves the motor slightly a different way, maybe 5 or 10 degrees, and it's going to come back to perfectly vertical trajectory. And I also designed every single part of the rocket using a 3D printer. And a 3D printer is really effective and efficient because it only costs, it's only a plastic, and plastic is cheap, and it takes about 10 or 12 hours to print the whole part. So if you messed up, you can redesign again and basically have another one next day. And I think this shows that how productivity is important when you make a rocket. And as I have a computer right there, this is a image of a computer, and the computer has 3 sensors: inertial sensor, barometer, and the SD card that holds the data. And this is interesting because the picture on the left-hand side is a inertial sensor that was used for Saturn V. As you can see, 3-axis gyroscope sensor, and it's massive. And that's the one that I have for my altimeter and inertial sensor, and it is as big as a quarter. So you can see how technology has come over the 50 years. But basically, you're doing the same thing. So the challenges, the amount of time was limited, and I could not successfully launch a rocket by today's presentation, which was a little bit unfortunate. And testing sensors and checking codes take a huge amount of time and require many attempts and failures. So while I was doing a altimeter sensor check, the altimeter kept showing me that the altitude of this campus was negative 50 meters, which makes no sense. And I was keep doing it, and it turned out that I have to have a connection with GPS satellite to show where I am, and I have to plug the default location altitude of where I am on the code and show where the rocket went. So the accuracy of the code itself, it took a lot of time to figure out why it didn't work and how it actually can work. And also one of the 3D printers broke, so I couldn't print out for a couple weeks. And also my initial thought of this project was I was trying to track the rocket itself because one of my rockets went missing, and I wanted to track where the rocket went. So I firstly thought that maybe I could have like a tile attached on the rocket so I could track it, but actually tile only works when you have your phone close to tile. But I wanted rocket where it went, which could be, the rocket could be gone like a couple 100 feet away from where I am. So I have to beam a radio control transmitter using antenna towards rocket for the whole duration of flight, which takes more than coding, which takes more than building a rocket, so I couldn't do it. And also, firstly, I thought the reusability is important for a rocket, so I wanted to bring the rocket using a drone, landing on the ground, and which also requires a PID control. And I thought that launching a rocket vertically and landing a rocket vertically where specific place was something that this whole industry is doing, and I thought that would be cool if I can do it. But it is possible to do it, but it just was not really feasible to do in this one trimester long project. So I'm a little bit disappointed that I cannot show you any explosions or videos here. But as I said, my initial idea for my project was to run a PID control and fly a rocket vertically, but I couldn't get to that point. But this project has taught me that how hard it is to do engineering, and the rocketry is also complex subject because you have to think about physics, mathematics, but not only mathematics, you have to think about stats like Kalman filtering, and also if you want to make a motor or engine, you have to think about chemistry as well. So rocketry is combining every single subject of STEM, and it was really hard. But this project gave me an idea and provided me the chance to take a glimpse of how hard but how fun it would be to do engineering, possibly in the future, in a couple of years in college. So I kind of proved that I can do what NASA did 50 years ago, but I need more time to actually fly a rocket with the computer, so I will attempt to launch next trimester. And that's my presentation. Thank you.
Do we have any questions for Kai?
Yep. What fuel did you use in your rocket?
Well, this fuel was using a chemical compound, and it just basically combustion, and it has a gunpowder on the top. And once I plugged conductor in a gunpowder just explodes inside a rocket, and it's just it's just the same compound as a fireworks, but a little bit more powerful. So the really hard thing about this rocket is that the thrust of the motor is constant for a whole duration of the flight. So only thing you can change is how the rocket moves. You're gonna change how weak or how strong you can control the motion, the thrust. So that's why this kind of like thing, the PID control is hard, because the thrust never changes, but because the thrust is powerful from t equals 0 to t equals something, the like vibration or the trajectory of rocket could go really crazy. Like my second attempt of flying rocket, it went like this and came back in. So that's why this PID control is important. But if possible, it's gonna be really interesting to make a few more, like maybe the first couple seconds it goes a little bit slow, but after like a couple 10 seconds it can go really powerful. That kind of like modification of the fuel components will be really interesting, I feel like. Yep.
What's moving on the rocket to adjust the yaw, the pitch, the roll? Like how are you translating the information from the PID?
So this is the motor, and the engine could go inside of this tube, and the tube is attached to this actuator, and the other gimbal is attached to the actuator. And basically so center of gravity doesn't matter because the only gravity is pulling down the rocket, but the center of lift, like how much the air is pushing the rocket, has like a lot of vector that can move the rocket. That's why you want to have an inertial sensor, and it measures an inertial sensor measures this angle, and also because the angle is constantly changing, you want to think about Euler angles as well as quaternions, and that's a little bit beyond my understanding of mathematics. But it is interesting that on this three-dimensional movement the rocket has to think about four-dimensional matrices.
So you're adjusting the orientation of the engine, the orientation of the motor. There's nothing external on the rocket.
No. It's just how much degrees you want to change it. Yeah, exactly.
Just to build off Mr. Palucci's question, there was another approach towards changing motion you were considering early on in the project. What was the other approach?
So the other approach to control the movement of the rocket is using a fins. So as you can see, Saturn V rocket also has fins as well, and my first rockets have fins, and the fins are important because it's important for a rocket to go vertically because it's splitting the air, and also it lowers the center of gravity. But not having fins is crucial because it's basically saying that you are not having any control over the rocket's motion. So I was also thinking that maybe I can put a motor on the fin. Each fin, there are 4 fins. So when the angle is put off, I can just move a fin a little bit and put it back on. But that's not really ideal situation because not a lot of rockets in the industry do this method. Most of the rockets like SpaceX uses TVC, which is just moving the engine. So I thought that maybe doing that would be more feasible. But yeah, that was another option.
Other questions for Guy? Thank you again.